first of all, thank you for the opportunity. Um, it's a real honor to be here among this selected group of people. I know you all, at least in paper. Some of you are just seeing for the first time in a long time. So good to see you. And I'm also humbled for the opportunity because I'm starting a little bit outside my zone of comfort. Usually, my main areas of research are tsunamis. I've been working with tsunami science for the past 10 years, and also remote sensing applied to the nearshore. But since we are a relatively small community in Chile, I'm lucky to be joined today by Pato Winkler, who I'm going to cite quite a bit, and by Raul Flores, I think he's also in the audience, another colleague. Sometimes we have to deal with different and several events at the same time. And so today, what I'm going to present perhaps is not going to be strikingly new for some of you. Oh, sorry, I forgot to share. But I think we have some particularities in Chile that make the system and the problem a little bit more interesting, even more interesting, I think. So I'm happy to present what we have been doing. That is mostly an exploration, and also to discuss and think about what it means for both countries and for coastal systems as a whole. So the name was a coastal cell blender is because we put everything in. And this is work mostly done by Daniel Rojas. He's a master's student working with me. And it began with a clear plan that never came to fruition. So we had to explore different alternatives. So I'm going to try to go over those today. So context, well, I guess you know where we are. We're just one swim away from you. It will be a very long one. This is what we're facing, just water in between us, between Chile and Australia. Well, we have New Zealand in the way, and probably Easter Island. But I guess not all the time we see that connection that clearly, in the sense that many of the processes that occur at the Pacifical scale perhaps ought to affect us in an interlinked way. So that's just to show where we are. We are at the opposite end. And if I look from my office, this is not Hogwarts. This is my university. I'm looking at the ocean. Well, that's not exactly true. My office is a little bit back, but I can see a corner of it. And it's a very interesting environment, and it's one of the main ports of Chile. It used to be the main port of the Pacific. And we have been, there is a lot of anthropogenic pressure on this system. The city has grown a lot, and our beaches are eroding, and that is not a particularity of where I live. It's also relevant in Chile as a whole. So this is another look of where we are. Chile, as I said in the abstract, is a narrow piece of land. In the narrowest section is only 150 kilometers wide. We are surrounded by the Andes. Here I'm looking towards the South Pole. So we are surrounded by the Andes that can reach up to 6 kilometers in elevation. And given that we have this very narrow strip of somewhat flat land, our rivers tend to be very energetic. On the other hand, we have significant upwelling from coastal waters, so that makes our seafood very, very rich if you want to come. But also we have a lot of tectonic activity. So that means that the Nazca plate is subducting under the South American plate, and that leads to the Andes, that leads to all the indentations that you see here. The pressure that we have from the constantly moving plates creates a very dynamic environment, at least at at time scales longer than the human. And we have energetic rivers. So we have this confluence of very strong swells, typically coming from the southern storm generation zone, very close to the Antarctica. We get swells traveling from North America, from the Alaska generation zone. And we have tsunamis, we have strong rivers. So we have a mixture of very energetic processes taking place here. So what is the evidence or part of the problem that we're seeing, and this is not typical of Chile, of course, is that our beaches are eroding. And Pato led an overview using the tool from the USGS, the DSAS, analyzing shoreline evolution of several beaches in central Chile. And it was found that when we add a tendons line, so just a line, we see that many of those beaches, 85% of those are eroding. And with current changes or actual states compared with the baseline, ranging between 1 meter per year up to 2 meters per year. So significant erosion. We have a couple that showed a little bit of accretion, and these are located very close to a gulf and a protected area. But most of the open beaches, or at least the ones that are clearly exposed to the Pacific Ocean, are retreating. So that's what we have seen over the last few years. But there is also anecdotal evidence and the perception that erosion has increased in the last decade. And during the last decade, we have had several events that are fairly significant and somewhat serendipitous in the sense that they occur all at during a very short period of time. We had extreme flood events, so that's why that cartoon is showing there. That created a lot of runoff and significant discharges and lots of affectation to urban areas. We had 3 earthquakes with their corresponding tsunamis, a few volcanic eruptions, forest fires, and Carolina Martinez and others analyzed this effect of the coastal erosion. So, and they asked a few years ago whether that's a new hazard that we need to take into account. When we look at this accelerated rate or this apparent accelerated rate of erosion, it struck us at first that it coincides with the aftermath in the region where most of the Maule earthquake took place. And note here that we are not talking about the tsunami, but the earthquake. And I'm going to get to that later on. What are the usual suspects? The wave climate, of course, because we have very energetic wave climate regularly. We can have up to 450 kilowatts per meter waves eventually. But with climate change, the combination of the two, Pato and others have been working on trying to incorporate the models from the IPCC and different scenarios to assess what is going to happen with our wave climate and our coasts. And one possibility or one expected situation is that we're going to have more frequent storm events. There is going to be a change in position where those events are being generated with a southward shift of the anticyclone that drives most of the wave generation. And that is also going to affect the mean wave direction. So as a result, it is expected that the beaches will pivot and also erode. And in this short video here, you can see that's up to 6 to 7 meter wave just breaking onshore, very close to the coastline. That was on 2015, one of the largest storms that we had here in this city. And that created a lot of damage. Also, usually we put in the can of culprits for this accelerated erosion, mesoscale variability, typically in terms of the El Niño Southern Oscillation, but with a strong focus on the oceanographic effects. That means that how Niño years change the mean sea level, and that's what you can see here. This is all part of the Martinez paper. And the correlation between the ONI index, the Ocean El Niño index, with the monthly mean sea level. So there is a variation in the mean water level that can also affect the relationship between mean sea level and beach processes. And also El Niño has been traditionally associated with stronger precipitation, more runoff, and more riverine discharge in coastal areas. Nothing this is new. We have events that have been extreme events in our history. We don't have a lot of records though, so the analysis that has been made suggests that they are becoming more frequent. But just this is one striking example. This is downtown Viña del Mar, where we live, and this used to be a pool, a public pool that that got destroyed on 10 August 1965, and rather the perfect return period for that storm was on August 8th, 2015. So almost 50 years to the day. Another very strong event, the same one that I showed before with the video, impacted the same area. The pool that I showed before was located exactly in this location, and then again we had the same or very similar level of destruction. So that's the overall setting. So beaches are eroding, and we were trying to further assess what is driving that erosion. So as a sample site, with Daniel, we selected Pichilemu, which is one of the hottest surfing spots in Chile. Is well known with regards to surfing, and the beach itself is Pichilemu, which is located here. It's a sort of parabolic beach exposed to the north. Punta Lobos is the location where most of the surfing takes place and where these two rocky outcrops are very famous. And as you can see in the southern south of the Punta Lobos, you can see a very long stretch of beach that is fairly well. It's very straight. That's what I meant to say. This is located in central Chile. Santiago, it's located somewhere around here. It's part of a long sort of network of somewhat small rivers and coastal lagoons that discharge. It's not a very populated area. So there is not a lot of human intervention on these systems. So that we thought it was very interesting in terms to assess just the natural processes instead of analyzing beaches that are located where we have a lot of anthropization and buildings and shielding of the runoff and the sediment supply. And it's located here in central Chile. And I think this picture is very interesting because it also shows that we have also a system of very large rivers that can have significant sediment plumes that discharge in the ocean. This bay is Concepcion Bay, and Pichilemu is located here, and Valparaiso is located around here. So I'm going to analyze that particular location, but later on we're going to expand our view. Well, why Pichilemu? Because a friend of Pato and then others suggested that after the earthquake, Beach 11 was eroding. And in particular, Nicolas Recordon provided a bunch of pictures that Pato put together, and where he was using fences that were placed as reference. This is someone who was just collecting information on its own. And when tracking the evolution, they could clearly see that the beach was eroding. So that's why we decided to analyze this particular location, and we use COSAT. Thank you. So say thank you to Killian for this. And we collected from 1998 onwards around 1,200 images, roughly 23 years. It's not a lot of time. We don't have a lot of data. And we analyzed Punta de Lobos. And to do that, we selected 11 profiles, cross-shore profiles, to see what the situation was on the beach. We also did a similar analysis in Kawil, which is the beach here. But I'm not presenting a lot of results for that today. I'm going to just skip over, run over this one. These are just the evolution. I'm going to show some more detailed images later. I think this is interesting, or it might be relevant later on, is the fact that we have most of our images are taken every 5 to 10 days, and almost 90% of those are spaced during that window, but occasionally we have large gaps because of lack of coverage. What is the total change between, that shouldn't be 2020, that should be 2000, and 2020, over 20 years, we have significant retreat as before, up to 60 meters in some locations, a little bit less in the northern portion, a little bit less in the south. So the beach is becoming a little bit more concave, if you want. That's the overall picture. We also analyzed whether there was some seasonality. So we took averages for the month over the 20 years, trying to analyze the changes. And here you see all the months in Spanish, January to December, and here are the profiles. So the profile number 11 is the northernmost, more exposed profile, whereas profile number 1 is the one that is close to the parabolic tip, closer to the Punta Lobos itself. So what we interpret here is that we have a certain degree of seasonality during our winters. June to August, the beach erodes more. In the northern section, it doesn't recover that much, at least from these measurements. So we have a persistent erosion that explains why it has retreated so much. But on the northern section, in the south section, sometimes we get more, we get a little bit of accretion, and then we get erosion, and then accretion again. So it's clearly seasonal. And there are certain profiles that seem to be a sort of pivot for the overall structure. But that's the average, and we didn't dwell in that. And this is because we wanted to see what happened with single profiles. And here things became at least interesting for us, because over the last 20 years, we sort of, when we eyeball it, of course, we can see a clear distinction between everything happening before 2010, where you can see cycles of accretion and erosion with larger erosion on occasion. But then we had a sudden retreat spanning just a few years, a couple of years. And then the system sort of achieved a new equilibrium with a very strong recovery, followed by a very strong retreat again, and it has been oscillating somehow. So so what we see is that there were different phases for this evolution. And it sort of coincides with the earthquake. So our first task was to, okay, what does the earthquake had to do with this? But before that, we went for the usual suspects. So we tried to analyze, and our original goal was to assess whether we could correlate wave properties or wave measurements over the past 20 years at that particular location, and then model and couple with the forecast for climate change and see what would be the evolution of the beach. That was our initial plan, to try to forecast a little bit. Problems, we didn't have a lot of data available. Waves, we didn't have actual wave measurements. Bathymetry was very scarce. We have a couple of bathymetric surveys, and that was it. We did have, however, one ADCP installed for a very short period of time. So we used that to calibrate our models. WaveWatch 3 for hindcast and forecast. And we got to the near shore using SWAN on a non-structured grid. And SWAN did a reasonable job. Here you can see the period of time we had in terms of wave heights. It follows the trend, the main trend, with waves reaching up to 3 meters on occasion. So the storm was well modeled. We had a little bit of a shift. We couldn't get better results, but we assumed it was okay. And so then we began to analyze anomalies and changes in the beach. So again, here, the top panel, you can see the time evolution of the profiles. And what we see is the relative change between profiles, between consecutive images. So that's why we have such a large value, because it's a sort of measure of the planform area between two consecutive profiles. Again, what we see is that before 2010, some portions of the domain were accreting, as others were eroding. But after 2010, we get more and more erosion systematically over the whole system. So there was a change. When we try to correlate that with wave power, here you can see negative wave power is because we are using the anomaly. So we estimated the mean wave power over the entire period, and then we try to, the idea was to see when we had less than the average and more than the average to see whether there were changes in the signal. As we can see, wave power was somewhat less than the average over the first few years. So, okay, there is an apparent correlation there. But it was followed by a season or a couple of years where increased wave power that could explain an increased erosion. But after that, and where we see a significant increase in erosion of the beach, we see more variability in terms of wave power. So it wasn't something that was sustained consistently throughout the years. It varied a lot more. So we couldn't find a proper correlation, at least, between these two. This is the analysis for wave height alone, and also for wave direction. We also try to see whether the waves were effectively shifting their position, and that could explain some of the rotation that we were seeing at some point. We couldn't find a good correlation, or waves alone were not a good explanation to what we were seeing. Again, that is the earthquake. So we also tried quantifying radiation stresses in order to use it as a proxy for the cross-shore transport and also the long-shore transport. Didn't work well. Then, since we had pictures every 5 to 7 days, we ask ourselves what is the proper time window to assess which wave conditions prompt the change. Since we're looking only every five days, we're going to see a significant change in, between the images, but that can be a result of the last couple of days where we had a, so we try with different windows and we're going to find anything. And the main problem is that we had a single bathymetry. Of course, the beach was evolving significantly, so we had a little bit of noise there. But we ask ourselves, okay, are we missing something? How about we try some other data or events to put in the equation? So we shift our goal and we try to see, okay, what is driving this variability? So since I've been talking about the earthquake, we went for the earthquake, first suspect. And here's something that, to some of you who are not or have not experienced these large earthquakes in person, these are drivers of significant coastal change in Chile. And part of the reason is that the earthquake is basically a release of energy, and that energy is elastic energy that the plates are creating between each other, and that creates a lot of deformation of the crust. And that deformation manifests on the coastline by an uplift eventually, or I forgot in English, subsidence. So there is a very nice paper of 2015 where they were able to use several bathymetric charts on an island, and they could measure that the island or the bottom of the ocean was changing relative to the sea level because of this continuous pushing down and then releasing and pushing down and then releasing. So the cycle goes as follows. So during the intervening the interseismic cycle, the coastline slowly goes down in this island. And then that means that you're basically charging in the same way as a trampoline. You're charging it down, and then it gets it releases its energy, and then it recovers to an upward location. So before 1835, there was an earthquake there, so it was down to 2.5 meters. It went all the way up to close to zero. It recovered a little bit post-seismically, and then it began charging again. 2010, it released it again. We have seen this cycle in several locations around the country. This is, for instance, for Playa Socos in Tongoy in central Chile, further north, where you can see this sort of bridge pier that used to get into the beach, and now after the earthquake in 2015, it went into the ocean. So significant vertical change. This is also the manifestation of the same, where we have before the earthquake a very wide beach, and after the earthquake that beach eroded, or because of this subsidence. In this case, the land went down. So when it goes down, the sea level, it can reach further inland, and then you have an erosive process. And in fact, in this case, they had to build protection, shoreline protection here, because it was eroding very, very fast. So, okay, the earthquake is there. So we went and looked for GNSS data, GPSs. Luckily, Pichilemu had one, but it was installed after the earthquake. And this is the projection, or here on the right side, you see an estimate of multiple published solutions for the vertical deformation for the 2010 event. You can see some areas of the coastline went up, so that's what creates the tsunami, and others go down. So most of the country goes down. But the coastline, in our case, is very close to the pivot line. So some locations go up, others go down, and there is a lot of variability. Vargas et al. Visited the country and collected measurements from different signatures that we can use to estimate this vertical uplift or change in vertical location. And we got up to 3 meters. So when we put that in perspective of what is going to be the relative sea level change or due to coastal climate change, that the projection goes between 30 and up to 1 meter for certain areas in Chile, and that is going to happen over 100 years, and you have a change that can be up to 3 meters in 2 minutes, it changes completely what we have to deal with. But it varies a lot in terms of the location around the in terms of the location along the coastline. So here you can see 3 meters uplift, and Pichilemu, our locational area of interest, only had 20 meters of uplift. But the problem is that it was uplift. So that means that that particular beach went up, and therefore more beach should have been exposed. So instead of seeing the erosion, we should have seen a little bit of accretion, because at least during the first part of the period, during the first phase of the recovery, because now you will have more sand exposed to be reconfigured. Anyway, we went to look at the GNSS data, and here are the actual measurements. Red and blue are the northward and eastward components. So what we carry is about the blue line, and this is after the earthquake. And you can see that we have a phase of co-seismic, interseismic subsidence. So it went up during the earthquake and then slowly went down gradually over a stretch of 2 to 3 years. And after that, it sort of began recovering again. We tried to use that information with what we were seeing in the erosion process. This going down actually could, or at least conceptually, we could use it to see an acceleration in terms of the erosion, but this going up didn't, because it means that the beach is recovering a little bit vertically. So therefore, more sand should have been exposed. Okay, so the earthquakes were not the obvious option. So we kept on looking, and now we went and tried to move further outside, and we began including other parameters such as the ONI, El Niño index, mean sea level series, sea surface temperatures, because we were looking for some measure of aesthetic change or changes in density that can also be correlated with ENSO signals. The specific decadal oscillation indices as well, and the southern annular mode we did not include. And when preparing the presentation, I sort of slapped myself because some should be included. Again, we couldn't find enough correlation with that. So we were running out of ideas, and we were missing the elephant in the room, right? And what is this? The mega drought. Since 2010, note the date, same as the earthquake, Chile has been subject of an increase or a very prolonged reduction in precipitation, especially in central Chile. We up to 90% reduction in river discharge. So that affects how much runoff we're getting from the Andes, and there are some research pointing that it has an effect on the ecology of the system. So people have been looking at in terms of the transfer between inland and coastal areas in terms of nutrients and others. But as far as I know, the connection with sediment supply hadn't been made. So what we did, we looked for the river discharge in several rivers. This is the Maule River, that large plume that you can see here. And there is another one that is called Mataquito that also has a somewhat large plume. And there is the Cowell Creek, located at the southern end of that straight beach that I showed before. These are located very far away. So 100 kilometers, 150 kilometers south of our area of interest. But we toss them in anyway. Why? Because they were part of this system of several beaches that there is not a significant feature on the shelf that can make us say, oh, these are separated systems. We have some very large canyons in Chile. There is the Biobío Canyon, the San Antonio Canyon, that can act as sinks for sediments and perhaps can separate the behavior in between them. But in the region that we were analyzing, there are none. There is not a single large canyon as the other ones that I mentioned. Folks that have been studying the mesoscale or large-scale climatology have noticed that there is some response of this turbidity measured from satellites, and there is an EOF mode that can explain most of the variability in terms of the turbidity measurements. In fact, Raul is working right now on in the Maipo River further north with these ideas. And so the area that we are interested in is located right in between. So, okay, let's see what these river discharges are doing, what is their behavior, and how that, or whether that correlates with what we were seeing. So these are some just eyeball examples. So the ONI, the El Nino oscillation, we had a very large ONI index prior to this period of accretion. So maybe there is some correlation there. We had mean sea level at several different stations, one further north, one very close to the area of interest, one further south. And down here, you can see the monthly flow rate. And as you can see, the monthly flow rate was significant before 2010, and then the mega drought began, and we get less and less and less, which is this year, it didn't rain at all. So that was just qualitative. So we tried to use a sort of more quantitative analysis without physics, just statistics. So we tried a linear combination of the different parameters. We tried brute force, multiple combinations, tried to see which one gave us the best correlation. And they were all somewhat in the same ballpark in terms of the correlation coefficient, up to 59 or 60%. Here are 40 of the correlations we used. And the one that we selected is the red one as the best. You can see that there are some other cases where you have stronger correlation, but we discarded those because those included the shoreline in Cowell. So that included two responses to the forcings. So we thought that was circular in logic after thinking a little bit about it. So that one that offers the best correlation considers the flow, the discharge of the three rivers, plus the mesoscale or Pacific scale indices, PDO and ONI. It includes the earthquake response and includes the wave power. So basically, all the processes that we somehow we can think are relevant. That was the one given the best correlation. And after doing that, we said, of course, it's obvious, right? So we know that we knew this from years that the river discharge is going to be significant. So why we didn't think of that before? And actually, it came as a surprise because it was so obvious. that I felt that we were not included in it. And at first, I looked at the just Chilean data or papers, whether the correlation between river outflows and beach erosion was made, none. But then it struck to me, or unless I'm doing something really, really wrong, it's not that often commented. It's not something that has been brought up or forward consistently, at least with correlation with climate change, for instance. We know that human interventions have been diagnosed as significant, let's say dams and others, but because it's clear, it's something that is very specific and you have a before and after. But with regards to slow evolution or droughts or decreases, gradual decrease in sediment discharge, at least unless as I said, we're doing something really wrong, I couldn't find a lot. However, those rivers are pretty far away. So that means that we need to think again our model or system, because we have some capes and cliffs, we have some beaches in between that we haven't analyzed. So now one of the questions we need to ask is what are the relevant or the dominant hydrodynamics for this sediment transport at a really large scale? And what is relevant as well is what is the proper cell? Because what we're seeing is that we have several watersheds discharging at different locations. We have several beaches in between. And it seems like there is a certain degree of response that is more broad and systemic than what we're seeing just one particular beach. And this is something that we are beginning to analyze right now, whether we see a transient response in terms of latitude. So if this is influenced by rivers that are located further south, do we see that this is as a wave, slow wave of erosion that propagates up and down the coast? When we look at the time series of Kawil, that is located just south of where we were looking at the first place, I don't know whether I'm doing wishful thinking or not, but you can see that the Kawil began this very strong response a little bit earlier than Pichilemu. So it seems like it began eroding, or this fast rate of erosion a little bit earlier and then became more stable. Human intervention, we don't know for sure, but it seems like it came before that than Pichilemu. So I'm shooting in the dark. I know that, but it's worth exploring. And a couple of days ago, Daniel came and he said, you know what? I used another river, one that is further north in this case. And this is the Maipo River. This is just south of Viña del Mar. So again, it's 150 kilometers north of our area of interest. But the Maipo River, which is in blue, has a relatively large, or larger than Mataquito at least, maximum flow rate. And it began decreasing in its intensities before the others. This is Mataquito and this is Maule. This plot shows that the ratio between the maximum flow rate per year with respect to the maximum in critical times, or at least for the time window used. So this is a relative plot to each maximum. Maule, the one that was showing that really large plume, has a flow rate that is about three times the other two. So it's a lot of water flowing in and perhaps sediments. But as I said, this was located further north, and most of the circulation models suggest that the mean currents should go north. So we were always thinking of sediment being fed into the system coming from the south and moving towards the north and getting to these beaches, and Pichilemu was somewhere in the middle. But when we threw in, and this is the result of the correlation when we superimpose all the data. When we have the first model that doesn't include the Maipo River, we don't see, for instance, that peak that happened in 2015, and we have a small shift in terms of the decay after 2010. If we include the Maipo that is located further north, we get a much better agreement in this area. So again, what are the dominant hydrodynamics and sediment transport mode? What would be the proper cell? Those are some of the questions that perhaps we need to begin asking and trying to address. And for the long run, can we forecast? Does this mean that we need to rethink our timescales and length scales for the processes when we look into beaches and even specific beaches? This is more a question for Chile. How should we add isostatic change to the sea level rise assessment? Isostatic, it means that resulting from tectonics. And perhaps for you, what is the role of these Pacific scale oscillations? When we look at the mega drought paper that is focused only on the precipitation, here we are, and here you are. And so this mega drought in Chile, it's affecting, as you can see, right where we have been analyzing our beaches. But you also have some level of dryness, I guess, in Northern Australia. And it seems like the Pacific Ocean as a whole is what is controlling these processes, and we need to see them more completely. And that's all we wrote. Thank you. So I guess it's more focus was food for thought mostly, and try to see where we're catching up. I don't know, Pato, do you think I left anything out? If you're still awake. He's not here. Okay, there it is. Thank you.